Hello. In this tutorial we will be discussing the concept of plasma, and I will also try to argue to you why should you care about plasma. Okay? Well, the primary argumentation is that for example, all the stars that we see in the night sky are in the state of plasma, which means that much of the visible universe is actually in plasma state. So if you don't understand the behavior of plasma, you don't understand much of the behavior of the visible universe. From the viewpoint of space weather, also our closest star, the Sun, is in plasma state. Here is imagery taken by Solar Dynamics Observatory of our Sun in the extreme ultraviolet wavelengths. And this shows a picture essentially of the atmosphere of the Sun. So the atmosphere of the Sun is also in plasma state. Further, also the solar transients are in plasma state. Okay, solar transients such as coronal mass ejections. Here is a picture taken by stereo spacecraft. This picture is taken using a coronagraph instrumentation. I'm discussing the coronagraphs and coronal mass ejections more in detail in other tutorials. But the basic idea here is that the solar disk is shown with this white line, and this moving blob here is a classic signature of a coronal mass ejection thrown from the solar atmosphere to the surrounding solar system. And also these coronal mass ejections are in plasma state. So really much of the space weather, much of the physics of space weather is also physics of plasma. So really from the fundamental viewpoint, in order to understand space weather, you need to understand the behavior of plasma. Okay. So with that, let's go discuss a little more in detail exactly what is plasma. There is a more kind of a general definition for plasma, which states that plasma is quasi-neutral ionized gas containing enough free charges to make collective electromagnetic effects important for its physical behavior. Okay. Well, how do we obtain this quasi-neutral gas in order to make these collective electromagnetic effects important? To describe that, let's start from sort of first state of matter. Let's draw a picture of that state over here. So let's call this something that is in solid state. Okay, solid. And what we do here for this solid block is that we apply heat into the system. Okay, let's heat into the system. Heat, and that heat will accomplish a state transition of this block into another state, which is liquid state. Okay. Right here, liquid. Oops. Liquid. Okay. We continue the same strategy here, so we apply more heat to the liquid blob, and we obtain third state of matter, which is gas. Okay. So let's draw here gas particles like that. So this is our gas that we obtain by heating the liquid. Now what happens when you heat the gas even further? It establishes or accomplishes yet another phase transition. Okay. So let's throw one more arrow here, apply more heat, and now the funny thing here, what happens is that Now in this gas, the matter or the individual atoms that composes the gas start to lose their electrons, which means that the matter starts to become electrically charged. Okay, so the matter becomes a collection of positive ions and negative electrons. Okay, so that's plasma. Plasma is really a collection of charged particles. Okay, and you can obtain plasma not only by heating gas, but you can obtain the ionization also, for example, in terms of electromagnetic radiation bombardment of the atoms, making up the gas and accomplishing the ionization also that way. All right. So this is our fourth state of matter, which is plasma. Okay, and now we have collection of free charged particles, and also in this case we have enough free charged particles to start making these electromagnetic effects important from the viewpoint of the behavior of the matter. Okay, so what does it exactly mean? Let's give a couple examples. Now, the fundamental physical force that dictates a lot of the behavior of plasma is, of course, Lorentz force. Let's just write one single equation here. Lorentz force, force equals charge times the electric field plus the cross product of the velocity of the particle and the magnetic field. Okay, so these are famous Lorentz force. So what this means, for example, is if you have an electric field here, that electric field will accelerate charged particles. For example, ions, positively charged ions, would be accelerated in the direction of the electric field. All right. So also plasma will react to the presence of the electric field in a similar fashion. Now, if we have a magnetic field, then the second term here in the Lorentz force accomplishes that the charged particles start to actually spiral around the so-called magnetic field lines. We define exactly what is magnetic field line in other tutorials. But the key point here to understand is that really once the matter becomes a collection of charged particles, the matter is not anymore electrically neutral. The electromagnetic field starts to play a very fundamental role from the viewpoint of the behavior of the matter. Let's give you another example that then has also very real-life applications from the space of the viewpoint. So let's draw here some kind of a structure for the magnetic field. Okay. So these are again magnetic field lines here, and it kind of accomplishes this kind of a bottle structure like this. Okay, and the magnetic field direction, let's say it's over here. Okay, so these are magnetic field lines of this magnetic field structure. Now, what happens in terms of the movement of charged particles in this kind of a magnetic field is that we have established a magnetic bottle. So the charged particles cannot necessarily anymore escape from this kind of a structure. They start to bounce and spiral around the magnetic field back and forth here. We have established a magnetic confinement. Okay, so these kinds of magnetic bottle structures can establish a confinement of the plasma. All right, so this is a really good illustration how electromagnetic field dictates or can dictate the behavior of the plasma. Okay, now we have many good examples of these kinds of magnetic bottles. These kinds of magnetic bottles from the space of the viewpoint. One of the classic examples is our radiation belts. Our radiation belts are nothing but a huge magnetic bottle. Let's bring in here illustration of that magnetic bottle. Let's make this a little bigger. So we have Van Allen radiation belts where we have quite high levels of charged particle radiation. And really how those belts are established are exactly through that kind of a magnetic bottle structure that I just showed you. So charged particles are trapped or are confined in these magnetic bottles inside the Earth's magnetic field, and that magnetic field bottle structure can then hold this plasma and this radiation in and become a hazard, for example, for spacecraft trying to fly through these types of regions. Okay, so really shortly, that's what plasma is. It's really a collection of a large collection of free charged particles, and because of that type of a collection of charged particles, electromagnetic fields become very important from the viewpoint of the behavior of the matter. And since a lot of space weather is physics of plasma physics, that is really, if you're interested in space weather and space physics, why you should care.